You press play, about 2 seconds later, the first frame appears. It feels like nothing. It's actually one of the most impressive pieces of infrastructure on the internet. And the fact that it feels like nothing is the whole achievement. Welcome back to Design Netflix. We have built continue watching and concurrent stream limits, both control plane systems, business logic on the servers. Today we cross into the data plane, the machinery that moves actual video. At this scale no cloud on earth can serve. Episode 3, what really happens when you press play. 3 things you'll walk away knowing. Why Netflix splits into a control plane and a data plane, why there is probably a Netflix server inside your ISP's building right now, and how the whole start sequence fits into 2-second budget. Let's get into it. Let's freeze that 2 seconds and stretch it out, because a shocking amount happens. At time 0, you press play. First the system asks who you are, what's your plan, and are you even allowed to watch this? That includes the stream check limit that we built in the last episode. Then it fetches decryption keys, because this content is encrypted and your device has to prove it's allowed to unlock it. Then the big question, fetch the video from where? Out of thousands of possible servers. And around the 2-second marks, the first frame renders. And here are 3 facts that sounds wrong but aren't. The video never touches AWS. The server streaming it to you may be physically inside your internet service provider's building, and the decryption key never once passes through JavaScript. 2 seconds, 3 planes of infrastructure. Let's design all of it. If you take one idea from this episode, take this one, because it's the concept the whole design hangs on. Netflix is really 2 systems with completely different jobs, and pretending they are one is how you would build something bad at both. The first is the control plane. Its job is to decide who you are, may you watch this, and exactly what should you play, which keys unlock it, and where you should fetch it from. Notice the shape of that work. Tiny payloads, kilobytes of JSONs, but a lot of thinking. And it runs basically once per play. That's the perfect fit for the cloud, and it lives on AWS. The second is data plane. Its job is to deliver, serve video segments, and honestly that's the entire job. But the shape is exact opposite. Gigabytes per stream. Thousands of requests over a 2-hour movie. And it's essentially 100% of the Netflix byte moves. The data plane is deliberately dumb. It doesn't know who you are. It doesn't run any business logic. It just serves the files fast. So why split them at all? Because smart and small scales in a totally different way than dumb and huge. One wants CPU, memory, and rich logic near your databases. The other one wants raw disk and network bandwidth close to the viewer. Force one system to do both and you get something mediocre at each. Split them and you can optimize each for exactly what it is. Every big streaming architecture rediscovers the split. Requirements. Functionally 3 things. 1. Start playback at any title, at the right quality of the device and network, and the right audio language, the right subtitles, and from the resume point we built in episode 1. 2. Enforce the rules on the way in entitlement, meaning is this title in your plan or your region, plus the stream limit check from episode 2, and crucially before a single video byte moves. 3. Protect the content. Studios license their catalog to Netflix on the condition that it's encrypted end to end. So DRM isn't a nice to have here. It's a functional requirement, a contractual one. Now the non-functionals, and these are where streaming gets its own personality. First, time to first frame, under roughly 2 seconds. That entire decision chain has to fit in that budget. Second, and this one's counterintuitive, rebuffer ratio near 0 matters more than fast starts. A slow start is small annoyance. The spinner in the middle of a tense scene is what makes people cancel. Third, survive planetary egress. Netflix video traffic is measured in double-digit terabytes per second. No single cloud region can physically push that. And fourth, degrade quality, never availability. Under stress, you drop 4K to HD to SD before you ever show an error. A worst picture beats no picture. Here's the boundary. The start decision gets about 2 seconds once. Delivery then runs for 2 straight hours. So you optimize first for the correctness and second for pure throughput. And that split is literally the architecture we are about to draw. Let's do one calculation that dictates the entire design. The bandwidth math. Picture a normal primetime evening. Tens of millions of concurrent streams. Let's be conservative and take just 20 million of them. At an average HD bitrate of 5 megabytes per second. Multiply that out and you get 100 million megabytes per second, 100 terabits per second, sustained for hours, not a spike. Now put that next to reality. A beefy server's network card pushes maybe a tenth of a terabyte. A large cloud region's total egress is single digit terabits, and the bandwidth bill to push 100 terabits out of cloud would be genuinely astronomical. So the math returns a hard verdict. You cannot serve this from a cloud. Full stop. Not it's expensive, it physically doesn't fit. Which forces the core idea. If the traffic can't cross the internet's backbone, don't send it across the back. Move the bytes to the viewers ahead of time. Pre-position the catalog at the edge, as close to each household you can get. And the scale is almost hard to believe. Netflix video has measured around 15% of all downstream internet traffic globally. At that share, you are not a CDN's customer anymore. You are an internet infrastructure. So Netflix built its own CDN called Open Connect. It's where 100% of the video bytes come from, and it's the single piece most candidates forget to mention. Let's design it. Here's the contract that kicks everything off. One request out, an entire playbook back. The client posts a /v1/playback/start with a title and what a device can handle, say 4K in HDR, and look what comes back. A session ID. That's the stream limit lease from episode 2. A resume millisecond, that's the row from episode 1. Then a manifest, which is the heart of it. A bitrate ladder, 4K, 1080 pixel, 720 pixel, 480 pixel. And the note that the whole title is chopped into roughly 4-second segments. A license URL separately for a keys. And there's a ranked of cached URLs to actually fetch the video from. Circle that. It's doing more than it looks. 3 things worth pausing on. First, notice the episodes just fused. In this single response, you can see E1's resume point, E2's lease, and this episode's delivery plan side by side. The series wasn't 3 systems, it was 1 system, and this is the seam where they meet. Second, a manifest is a menu, not a file. Every title is pre-encoded into that whole ladder of qualities ahead of time, sliced into 4-second chunks. That pre-work is exactly what makes switching quality and seeking cheap later. The player just picks a different rung for the next chunk. And third, those ranked URLs mean failover is backed into the contract itself. The player gets 3+ caches. Best first. If the top one dies mid-movie, it just slides to the next one. No new callback to the control plane. No spinner. We designed the recovery before anything broke. So what is Open Connect physically? Let's start with the box, then where the boxes live. The box is called an Open Connect appliance, an OCA, a purpose-built server running a custom FreeBSD and NGX stack. A modern one holds up to around 560 terabytes of flash and sustains 100+ gigabytes of video output. And it does exactly one job: serve encrypted segments over HTTPS. No business logic, no idea who you are. That radical simplicity is why one box can push so much. Now the clever part. Where they sit. The best case is an embedded OCA. Netflix gives the hardware for free to qualifying internet providers to place inside the provider's own network. Think about what that means for you. Your video segments never cross the internet's backbone at all. They come from a rack in your ISP's building, one hop away. The ISP saves an expensive transit bandwidth. You get local network latency. Genuinely everybody wins. For ISPs without an embedded box, there are bigger OCA clusters at internet exchange points, the buildings where networks physically interconnect, and those also act as the fill source for the embedded ones, and control stays with the ISP. An OCA only serves the IP ranges its provider announces to it over BGP, so the provider decides exactly which customers its box serves. But here's the trick that makes the whole thing work, and it's the opposite of a normal CDN. A classic CDN caches on demand. First viewer takes the slow path, everyone after gets the cached copy. Open Connect doesn't wait. Every night off peak, each OCA proactively downloads what its local population will probably watch tomorrow. Popularity predicted region by region. So by morning, the catalog is already sitting one hop from your couch. Cache misses aren't handled quickly. They are designed out before anyone presses play. This is the entire bet of the architecture. Move bytes early so you never scramble to move them fast. Okay, dozens of OCAs could serve you. Which one do you actually get? That's the steering service, and it's basically matchmaking a viewer to a cache. It weighs 3 things. First, where are you? Not your street address, but your network location, your IP, and the routes your ISP announces. Because on the internet, Distance is measured in network hops, not miles. Second, who actually has the title? Every OCA continuously reports its inventory upward, so steering knows exactly which boxes hold which content. Third, who's healthy and has headroom? Constant telemetry on load, capacity, and link health, so no overloaded or sick boxes gets handed to you. The steering service itself lives up in a control plane on AWS, and it runs once per play. It takes those inputs and returns a ranked list. Number 1, the OCA embedded in your own ISP closest has the title healthy. Number 2, an exchange point OCA, one network hop further out. Number 3, a regional cluster, the safety net, best first, fallbacks behind it. And here's the design lesson that echoes the whole series. Steering decides once, then hands the player a ranked list and gets out of the way. Failover afterward isn't a new decision or another round trip to the cloud. It's the player quietly walking down a list it already holds. Decide once, delegate the rest. That principle keeps the expensive smart part off the hot path. Let's assemble the whole thing, and I have drawn it as 2 bands so split is unvisible. Top band, the control plane on AWS. Your press play hits Zool, our edge gateway from the earlier episodes. Authentication and rate limiting takes place there. Behind it, the playback service is the orchestrator, and it owns that 2-second budget. Its trick is to fan out in parallel whenever it can. It checks entitlement and the episode 2's stream limits first. So if you're blocked, it fails fast and cheap. In parallel, it lines up the DRM license and asks steering for your ranked OCA list. Then it assembles one response and step aside. Everything in this band is once per play. Tiny JSON, heavy thinking, then done. Bottom band, the data plane, open connect. The true source of every encode is object storage S3, the origin. Overnight that fills the exchange points OCAs, which fill the embedded OCA inside your ISP. And then the only heavy arrow on the whole diagram. Encrypted 4-second segments streaming over HTTPS from that local box straight to your player for 2 hours. Step back and look at what's not connected. AWS never touches the video byte. A control plane decides, a data plane delivers, and the 2 planes only actually meet inside your player. That separation is the design. Let's watch the clock actually tick, because a 2-second budget only works if every millisecond is accounted for. Time 0, the player post playback start. Inside the service, 4 things happens at once, not in sequence. Entitlement, the stream limit reserve, the resume point read, and steering. Parallel, up because we cannot afford add up 4 latencies. Around 300 milliseconds, back comes one response, manifest, license URL, 3 OCA URLs. Next, the player requests the license and it attests itself, proves what kind of device it is, and that's it's legit. Around 600 milliseconds, the keys come back and they go straight into the CDM, never into the app's code. That CDM, the content decryption module, is a sealed box built into the device. Keys go in, decoded frames come out, and even Netflix's own app can't read the keys. That's the studio contract, enforced down in hardware, and it's why screen recording a Netflix stream gets a black rectangle. Now the control plane exits and the data plane takes over. The player requests segment 1 and deliberately at the lowest bitrate. Around 1.2 seconds, 4 seconds of the video arrive from that OCA one hop away. It grabs segment 2, 3, 4 to build a safer buffer, and right around 2-second mark, first frame. It started fast precisely because it started small. Quality climbs from here. That start small climb fast behavior has a name, adaptive bitrate, and it's how you get 2 hours with no spinner. Watch one stream over time. Segment 1 is cheap 480 pixel. That's the instant start. As the buffer fills and the network proves itself, the player climbs the ladder, 720, 1080 up to 4K. Then mid-movie, the Wi-Fi dip, and instead of stalling, the player just steps quality down a rung or 2. Network recovers, it climbs back. The picture softened for a moment, the video never stopped. 3 things make this work. First, and this flips the usual model, the client is the decision maker now. No server tells it what bitrate to pull. Each player watches its own buffer and measured throughput and pick the next segment's quality itself. That's millions of tiny independent control loops with zero central coordination, which is the only way this scales. Second, the buffer is your resilience budget. 30 seconds of buffer video means the network can completely vanish for 30 seconds before anyone sees a spinner. The player spends that budget to paper over every hiccup. And third, remember those ranked URLs. If the OCA itself dies mid-movie, a segment request times out and the player reissues it to OCA number 2 from the list it already holds. One segment arrives late, the buffer absorbs it, and the control plane never even finds out. Failover with nobody in charge. Last phase, the failure modes. And notice the theme running through all 4. Give up quality, never the movie. 1. The rare cache miss. The nightly fill mispredicted, and the title suddenly goes viral. No problem. The player just uses the URL 2 or 3, an exchange point or a regional OCA that does have it, and that request quietly fills the embedded box in the background for the next viewer. A little further away, still no error. 2. Steering is degraded and can't compute your perfect OCA. Fall back to a good enough default, a regional cluster by geography rather than blocked playback. A suboptimal cache is invisible. A failed steering call is a black screen. Never trade the second to avoid the first. 3. The license service is slow, and this is the honest exception to degrade everything, because DRM is one hard gate. No keys, no playback, no contract, you cannot skip it. So instead you make it never the bottleneck, aggressively cache device attestations, set tight timeouts, run it as its own replicated fleet. When you can't degrade a dependency, you over provision it. And 4. The thundering herd. 10 million people heading 1:08 PM premiere. Because the whole catalog was pre-filled before launch, that premiere is just reads off local flash on thousands of OCAs, not a stampede against a single origin. The entire architecture is one long bet that moving bytes early beats moving them fast, and the herd is where that bet pays off. 4 patterns to steal, and they travel far past Netflix. 1. Pick the control plane from the data plane. Let smart and small decide, dumb and huge deliver, and scale each on its own term. 2. Push content to the edge early. Prediction based pre-filled beats fetch on demand, because the best cache miss is the one that never happens. 3. Decide once. Hand over a ranked list. Keep the expensive brain off the hot path and let the client fail over on their own. 4. Degrade gracefully. Drop the bitrate, pick another cache, surrender quality long before you surrender availability. Next episode is the finale, and we tie a bow on the whole series. First, trending now, real-time top K at massive scale, using a beautiful little structure called a count min sketch. And then we take all 4 episodes, continue watching, stream limits, playback and trending, and assemble them into one giant Netflix architecture diagram live. If you learned something, like and subscribe so the finale finds you, and tell me in the comments, did you know the video never touches AWS? See you in the last one.